One of the important things to know about aroma compounds, if you're using them to study them, to make your own fragrances, or if you use them as flavors, you have to know how to protect aldehydes. Now, aldehydes, as it so happens, they're very sensitive to oxidation. And some of them can oxidize just in air, just in a few hours, they can go bad. I learned this the hard way. So here I have aldehyde C8 or octanol. That's a little bit smudged. And this is a 10% dilution in ethanol. 10% is about your minimum effort that you can do. You can store it at this dilution. To use it in perfumery, generally you want the aldehyde to be about 5% or even 1%. You want it to, because they have a lot of effects, so you want it to not overwhelm the formula, the recipe. Now this really has its own smell. It's got that fizzy sort of carbonation champagne note that is referred to as aldehyde. But under that, it's not really orange, it's not really cheesy, and it's not really mushroomy. It's just sort of its own thing. Now, the molecule for that is this. Now, this particular aldehyde will go rancid very quickly when exposed to air, a few hours. And what happens is you get an atom of oxygen. Now, in air, the oxygen is diatomic. So each molecule is 2 atoms. So each molecule of oxygen in the air can ruin 2 molecules of aldehyde. And what happens is the oxygen forms a bond to this carbon, inserts itself between the carbon and the hydrogen, and we have octanoic acid. It's also called caprylic acid, after the Latin word for goat. And it has a goat type smell. It's cheesy, rancid, fatty, waxy. So I've got the original container that the octanol came in, and it's empty. I've emptied it all out to dilute it, but of course there's still a little bit of residue in there. I haven't washed it out. And this has only been a few days, and most of that time it's been closed. And smelling it, it's very definitely fatty, waxy, cheesy, rancid, goat-like. It's just not good. Now I have this other aldehyde MNA, methylnonyl acetaldehyde. This is diluted to 5% in ethanol. And this just smells delightful. It's waxy, it's aldehydic. It's a little bit like lemon lime soda. You might see that comparison made. I didn't build the molecule for this. It's similar to the octanol, but it's a longer chain. It's got a methyl group near the aldehyde end. This is certainly one of my favorite aldehydes. When it oxidizes, when it goes bad, it smells disgusting. Just like stomach turning, sour milk, just awful. I did not save the bottle that original came in because I've smelled that already, and I just don't have to go through that again. Just no. Now I have citral, diluted to 10% in ethanol. This is naturally a component of lemons, lemon peel, lemon oil. And in this dilution, it smells delightful. It's very peely, and it's got that sort of sparkle that fresh lemons have, or that good lemonade has, not the artificial crap. So that's from naturally occurring citral. I have a molecular model here of citral. As we can see, it's somewhat like the octanol, but it's got these double bonds in it, and it's got these methyl groups branching off of it. Now, this bottle that the citral came in, it's been a few weeks, and I had it open most of the time. Now, smelling this, it's musty, maybe a little metallic, it's weaker. It's lost its sparkle, it's lost that great quality, that wonderful quality that lemon has, that fresh lemon has, just gone. It's still got this sort of a citrus character, but it's just not good anymore. Citral is 2 different isomers, and it occurs in a lot of plants and a lot of the things we eat. What ratio of isomers you get depends on the plant, but one of the isomers is this one, geraniol, and the other one is called neral. Geraniol, which is the alcohol equivalent of geraniol. For that, you would have another hydrogen on this carbon. This would be a single bond. You would have a hydrogen here. Geraniol gives you the scent of geraniums, but when geraniol, component of citral, oxidizes, it oxidizes to geranic acid. That's where you get that musty, spoiled, no more good smell. But the fact that it took longer for the citral to oxidize, I wonder if that might be because it has these double bonds in the chain, and it has these branches. And aldehyde MNA is also branched, so that might not even be a factor, but the double bonds at least. I don't know why. I haven't found information on why this happens, why these seem to be more stable than just the aliphatic, just the full of hydrogen kind. But that's one thing I've observed. Citral is a natural component of lemon oil, and lemon oil will also oxidize, will also go bad quickly in air. Now, acids catalyze the oxidation of aldehydes. So as you have an aldehyde that's exposed to oxidation, to air and oxygen, it's going to generate a little bit of acid at the surface, and then that's going to catalyze further reaction, and so the reaction is going to speed up. Now, the citral that I have took a few weeks to get smelling bad. But if you have a lemon, if you leave a slice of lemon cut open, exposed to air, I really like eating lemons, limes. I enjoy the sourness. If you leave it sit overnight, it's not going to taste good after that. And that flavor, the way it turns, the way it goes bad, that's the same thing I'm smelling here. That it's weaker, metallic, musty. Lemons are full of citric acid, and that's why they're so sour. And so that acid, I'm guessing, probably catalyzes that oxidation of citral. So while it took a few weeks in here, in this bottle, with no citric acid, for this residue to start smelling bad, it's easy to see how, in the presence of the natural acid in lemon, it could, the reaction could happen a lot faster, such as overnight. Now, another aldehyde, a very common one, is cinnamaldehyde. And it's exactly what you're probably picturing. This is diluted 10%, and it just smells amazing. It's used as a flavor. It's the smell and taste of cinnamon candy, like those hot cinnamon candies. This gives you not only the aroma and flavor of cinnamon, it gives you the heat, that spiciness, and so it's a very good flavor. It naturally occurs in real cinnamon. It's just this amazing thing. Now, this is the molecular structure of cinnamaldehyde, and we have this double bond here. We also have over here this benzene ring, and benzene rings, as it turns out, are very stable. They're called aromatic, even though technically all of these molecules have an aroma. Aromaticity in chemistry is a different thing, it's a specific thing. And it's very hard to break this ring apart chemically. As to whether or not that stability extends to the aldehyde group, again, I don't have that information. It seems to, from my observations, because this was also left out open for a few weeks just to let the air get in and oxidize it. And the smell of it, so this would be oxidized to cinnamic acid. It's still cinnamony, and it kept its cinnamonness for a long time, for probably longer than the others kept their uniqueness. It's less spicy now than it was. It's more resinous or like gummy, like if you've ever smelled gum benzoin, it's a little closer to that. Or a little more aspirin-like, or what they call salicylic, even though there isn't any salicylate in this. But one striking thing that happened to this, it turned solid. It's all solid in there, in the back. And you can see around where the cap goes. One of the perfume aldehydes, C12, or lauric aldehyde, is just a string of 12 carbon atoms, an aldehyde group, is also, it's notorious for solidifying when it oxidizes. Now, cinnamaldehyde oxidizes to cinnamic acid. I have another aldehyde here that's used for fragrance. It imparts a sea breeze. It's called floral ozone. This I have not diluted. This just smells just as good, wonderful, as it did when I first got it 3 years ago. It's breezy, it's airy, light, and aquatic, watery. It's used a lot in aquatic accords, in perfumery. It's a little bit plasticky, and I think it's glassy. And then under that, at full strength, it's got this peony-like sweetness, sweet floralness to it. So it's easy to see how it got its name. It's floral smelling when it's strong, and it's ozone-like when it's dilute. Now, the fact that this hasn't gone bad despite 3 years of being in a bottle with air, exposed to air, we can see from the molecular structure that floral ozone is an aldehyde. It's got this carbon double bonded to an oxygen, bonded to a hydrogen. It's bonded to only one oxygen. But even though it's an aldehyde, it hasn't gone bad. And I don't know if it's because it's got this benzene ring. I don't know if that stabilizes it somehow. I don't know if the acid version may be odorless. Like if I take and put the oxygen and oxidize this molecular model, that this compound might be odorless. It should at least solidify, shouldn't it? And it hasn't solidified. But I find this very interesting. Another similar aldehyde to this is cyclamaldehyde. Also doesn't go bad. Or I've had it a few months, it hasn't gone bad. So that definitely seems to be a pattern where the aliphatic, the fat-like or oil-like, the fatty aldehydes, oxidize very quickly, and the aromatic ones don't, or not as quickly. Well, I hope this has been informative. We've looked at aldehydes in fragrance use and dilutions, and we found the reason why lemons, fresh cut lemons, exposed to air, they start to go bad, or why lemon oil does the same thing. It turns not so good. And we've looked at the molecular structures of these aldehydes and found that the ones with the straight line of saturated carbon atoms are less stable to oxidation than the ones with double bonds and with aromatic rings. Thank you for watching.